0.62 is the binomial probability distribution, and what it is, it's a specific kind of discrete. So the ones we saw on Wednesday were just like random. How many classes were you taking? What's the probability of making a free throw? All that kind of stuff. Where the binomial is specific, and you'll see why, because what's the prefix bi mean? 2. So what we're going to realize is that these experiments that have 2 outcomes, there's a quicker way to do it than just this huge chart, all right? So it says many types of probability distributions have only 2 outcomes. Flipping a coin, what can you get when you flip a coin? Heads or tails, 2 outcomes, right? Shooting a free throw, how can that be 2 outcomes? Yes. And then what about gender of babies? Yeah. But I want to point out these are obvious ones that have 2 outcomes, but you can make basically anything a binomial experiment having 2 outcomes if you focus on what you want to happen and then everything else is the opposite. For example, getting a grade in this class. You can get an A, B, C, D, F, or a W, but you might say pass or fail, right? And so A, B, or C is okay, and then anything else would be a fail. Or you might say get an A or anything else. So there's a wide variety of things where it's not just 2 outcomes, but you can kind of narrow it down to 2 outcomes, all right? So if an experiment that has only 2 outcomes and they meet a certain criteria, it's called a binomial experiment. So let's see the criteria that it has to meet in order to be a binomial probability experiment. The first one is the experiment must be performed a fixed number of times. So you must know your N, guys. You can't just say, I'm doing this forever, or I did it a lot, and you didn't specify how much a lot is, okay? You have to know your N. Each time you do the experiment, it's called a trial. So, it's basketball season's rolling around, right? So say we're shooting free throws. Each free throw you would shoot would be considered a trial, okay? So if you shot 10 free throws, your N would be 10. You had 10 trials. What else must have to be true? The trials must be independent. Do you guys remember what the word independent means? By themselves, like you do it and it doesn't affect anything else, right? So this kind of says it. It means the outcome of one trial will not affect the outcome of the other trials. So when you have a baby, there's no specific thing, like if you have a girl first saying that you're going to have a boy next, right? They're independent events. You can kind of argue it when it comes to like free throw shooting. So we have to just assume that we're great free throw shooters. We're not scared. If we miss the first one, it's not going to throw us off at all, that kind of idea. All right, each trial, there has to be 2 mutually exclusive outcomes, okay? It's either a success or a failure. And they use the word success and failure not necessarily as the good and the bad. Success is what you care about, and failure is anything else, okay? So care about, and then this is anything else. So maybe the coach is really focusing on the amount of free throws you missed to know how many laps you have to run. So success would be the missed free throws, and the failures would be the made. So again, success and failure is not always that positive, negative atmosphere. It's what you're focusing on versus anything else that could happen. All right, last one, the probability of a success is the same is the same for each trial. And that kind of goes with the independence. When you do it the first time, you're a 90% free throw shooter, so you're still a 90% free throw shooter when you go to make that second one, okay? So the definition that we're going to fill in is if this is true and we actually meet all these criteria and we are part of a binomial experiment, the X is called a binomial random variable. So he's a special variable that we haven't talked about, but really just that adjective binomial, right? A random variable we've talked about. It's something that occurs by chance, right? And so this binomial not only occurs by chance, but it's part of a certain experiment where there was only 2 things that could happen, okay? So the first couple problems on your homework for 6.2 are going to give you situations where you have to ask yourself, is this a binomial random experiment? Yes or no? If so, they're going to ask you what N is, what P is, and all this stuff, okay? So let's go over some of the notation. N is always the number of trials, but guys, hopefully that's nothing new, right? N is your sample size, so if you're shooting 10 free throws, that's 10 trials. N is still kind of that representation of a number, okay? So N is how many trials you have. P, little p is denoted the probability of a success, okay? So if you're a 90% free throw shooter, P would be 0.90. So what's the probability of a failure? If I was a 90% free throw shooter, what's the percent chance I'd miss it? 10. So notice they're just denoting the failure as the complement, 1 minus P. They don't give it a new letter or anything. It's just, hey, if you know you're a 90% free throw shooter, you're a 10% chance of missing it, okay? So 1 minus P, guys, 1 minus P, we'll maybe box in our, 1 minus P is the probability of a failure. So it's kind of like those ones we did in 5.4 and 5.3, that when they give you 1%, they've really given you 2 percentages, right? All right. X is the number of successes, so that's what you care about. So if I want to know the probability of making 8 free throws, my X would be 8. And last but not least, this is kind of like a weird, like I feel like they make it look more complicated than it really is. But if X is the number of successes, then X could be the least 0, right? You can't make negative amount of free throws, but it can't be more than the number you're shooting. So X has to be somewhere between 0 and your number of trials, right? I can't make 12 free throws if I'm only shooting 10. Wouldn't that be cool? Okay. But most likely, guys, it's some number between, okay? So let's look at this first one. It says, a card is drawn from a deck. A success is for that card to be a heart. So what does that mean for a failure? Any other suit. So notice when you draw a deck of cards, there's 52 things that can happen, but they're narrowing it down to 2 things. You either go to heart or you don't, okay? The cards put back into the deck, that's important, okay? We'll talk about that in a second. A second card's drawn from the deck with the same definition of success. Did you get a heart or not? The second card's put back and so forth. We do this 10 times. The question is this a binomial experiment? Yes or no? If so, what is the number of trials, the probability of success, and so forth? So I'm actually going to follow this criteria. Step number 1. Do we know the number of trials? I'll come down so you can see both. Do we know how many times this is being performed? 10. We do. So right there, we know the number of trials. So let's do N equals 10 trials. So we can check mark criteria number 1. Criteria number 2, are the trials independent? And remember what independent means. It means when you do it the first time, does it affect the probability of the second, the third, the fourth, and so forth? What are we doing in this experiment? Are we rolling dice, shooting free throws? What are we doing? Drawing a card. But once we draw the card, what do we do with the card? Put it back. So if we put it back, have we changed the probability of getting any other card? No. So they are independent, right? Card is replaced. So we do know that it's independent. Guys, if it said the card's not replaced, right there, you would stop. You say, this is not a binomial experiment. I've messed up my probabilities. I don't need to keep going. Number 3, is there a defined success and a defined failure? There sure is. What was the success? Heart. Getting a heart. What was the failure? Anything else? Any other suit? Check. I'm getting kind of low. All right. And then step number 4. If you look up here, it says the probability of a success is the same for each trial. What's the odds of getting a heart? How many suits are there? How many suits are there?
4.
4, right? And if I'm always putting a card back, isn't there always a 1 out of 4 chance? Yeah. So how do we word that? Probability the same each trial? Question mark? Yes. P equals 1/4 or 0.25, right? So since we did 4 check marks, we met all 4 criteria. Is this a binomial experiment? Yes. So what's sad is that we do all this work, and that's just answering this first question. Is it a binomial experiment? We've kind of answered the other ones in there, but we'll go back and make sure we've done all of it, okay? So if you know the number of trials, and that each trial is independent and the probability doesn't change, and you know what a success and failure is, you have a binomial experiment. So let's answer these questions real quick. Don't flip the page yet. If it's yes, they're going to ask you, what's the number of trials? Didn't we already answer that right here? 10 trials, right? What's the probability of a success? What's the probability of getting a heart? Don't we have that right here? What's the probability of a failure, though? 3/4. How'd you get that? It's just a complement, right? So if you can be happy with one of the 4 suits, you would be unhappy with 3 of the 4 suits, or 75%. Is that okay? There he is, okay? And what's the last thing that we haven't done yet? The possible values for x. Remember, the possible values of x just fit this. The only thing you have to fill in was how many times were we doing this? 10. So x has to be somewhere between 0 and 10. So I circled the questions that they asked us. We know the number of trials. We did it 10 times. The probability of success was one of the 4 suits, or 25%, which left the probability of a failure, the complement, 75%. And the possible values of x, I knew that great less than or equal to 10. I just put a less than sign. The odds aren't very good, but all 10 cards could be hearts, or none of the 10 cards could be hearts, but most likely be some number in between, maybe 4 hearts or 5 hearts, okay? So that is a binomial experiment. On a test, if I have you do this, I would give you these 4 things. I would give you the criteria. You don't have to memorize those. You would just need to know to go through them like we did here. Does that make sense? So like when I say the number of trials, you're like, okay, that's N. We did it 10 times, that kind of idea. So let's look at the top of page 5. I don't give you a whole lot of room. I wonder why. Let's see here what's going on with this one. It says, 3 cards are drawn from a deck without replacement. The number of aces is recorded. So number 1, do we know the number of trials? How many times we're doing this? We do. How many times are we doing this? 3. So N equals 3 trials. So number 1 is met. Number 2 are all the trials independent. Why not? Without replacement. That's your key word, guys. If we're not replacing them, the second you draw 1 card and don't put it back, you've changed the probability of all the other ones, okay? So this is no, so it's not a binomial. We don't even care if number 3 and 4 are met. The second you don't meet one of them, you do not have a binomial. Okay? And those are really quick, yes and no. You don't have to answer the other parts, like N, P, and all that kind of stuff. All right? So what I'm going to get into now, this is like where like people are already falling asleep. You're really going to fall asleep on this one, is whenever I can prove to you guys where something comes from, I like to. I think a lot of people go into math thinking it's just magic, like someone made this crap up, right? Like, poof, like they have a wand, right? So we are actually going to derive the formula, believe it or not, for a binomial. So let's say I have an example with just 3 things, okay? I'm just shooting 3, I'm really bad at basketball, okay? So let's do a really easy example where I'm just shooting 3 free throws. And the probability that I make it's 40%. Ew, I'm not on the basketball team, okay? So I want to know if I'm shooting 3 free throws and I'm a 40% shot, what's the probability that I make 2 of the 3, okay? So first of all, let's just think of the arrangements. Do I care what order I make my 2 shots? Do I care? No. So what's one order I can make 2 free throws out of 3? The first 2 and then miss the 3rd, right? So that would be called success, failure. Do you guys agree with that? What's another arrangement? Miss, not the first 2, miss the first 1, right? Because I want to make 2. I missed the first 1, but then I make the last two. What's another arrangement? You got it. I could just miss that one right in the middle. And you guys are going to quickly see why we want a formula, because this isn't hard to derive with just 3. But just think if you're doing 10 times, how many different arrangements you can make 3 out of 10. That would be horrible, right? We're rearranging. So we're just doing it with a little small number. All right, so let's use these exact same arrangements down here to figure out our probabilities, okay? So let's just focus on that first one. Do you guys agree that when I shoot these, they're independent, right? So what's the probability of making that first free throw? They told me. 0.4. What's the probability of making the second free throw? 0.4. What's the probability of missing the third one? 0.6. And you guys agree that we're doing multiple attempts, so it's just the multiplication rule from chapter 5. So this is just going to be 0.4 times 0.4 times 0.6. Is that okay? All right, let's think of the second scenario. The second scenario starts with a miss. What was the probability of missing it? 0.6. But then what's the probability of making the next two? 0.4. And you guys are going to see something happening, right? All right, last one. I make the outer two, but I miss the middle one. So what arrangement will that be? Yep. Is that okay? So what do you notice about all 3 scenarios? All 3 scenarios have how many 0.4s and how many 0.6s? 1, right? So we could write this as 0.4 to the second power times 0.6 and figure out what that is. What do you guys get when you do that? All right. So the probability of making 2 free throws would be 0.096 for the first arrangement, 0.096 for the second arrangement, and 0.096 for the third, right? Because this is the probability of this or this order or this order, right? Or means add. So if each of these are 0.096, I'm going to add them all up. Or what can I do? Take 0.096 times 3. What do you get? What's 0.096 times 3? I have 288. Does that look right? Anybody? Does that look okay? It's pretty low, but don't you guys agree if I'm only a 40% shooter that I probably wouldn't make a majority of my shots, right? 2 out of 3 is more makes than misses. So the odds of me making 2 out of 3 is pretty low, all right? You guys just calculated the formula, and I know you don't feel that way, but you did. What's a way to show this, okay? Right down here, we already did all this, but I want to show you exactly what we just did, okay? How do we show that there's order doesn't matter? Do you remember the counting technique where you choose a few from many, but order didn't matter? What was that called? Anybody? 5-5? Permutation or combination? Which one order didn't matter? Combination, right? So if we do 3 choose 2, this is a quick, easy way to figure out and how many ways can you make 2 out of 3. So guess what you'd get if you did 3 choose 2 in your calculator? You get 3, right? We have 3 different orders, okay? Then what did we do? We said, okay, times 3, how many successes did we have? 2, so we had 0.4 to the second power. And then how many failures did we have? 1, so we had 0.6 to the first power. If you put that in your calculator, guess what you get? You get the 288, okay? So what we're going to do is we're going to take this exact same formula that we just derived and look at how it's exactly like the top, okay? So after you get this written, I'm going to leave mine down here, but you go ahead and flip yours to the top of page 6. And let's see if we can make sense of the top of page 6. So it says the generic binomial. So we did it with a specific case, but the generic binomial probability distribution, it says the probability of obtaining X successes, so that's what you care about, in N independent trials, that's how many times you're doing it, of a binomial experiment, where the probability of success is P is given by this formula. So notice it has the combination in front. That combination in front is always going to be how many different ways can you make 2 out of 3 free throws, right? So what did we have? How many total free throws we had? 3, and how many we were concerned about making? 2. So that's why on your formula, you'll see N, how many total, and then X, how many you care about making. The next thing on top of page 6, what do you have? You have P. What's P stand for? The probability of a success. What was the probability of our free throw? 0.4. But how many were we worried about making? 2. And notice yours is raised to the x power. How many successes you have. But if you only are making 2 of the 3, that means you're going to miss 1, right? So we have 1 minus P, or the complement, 0.6. 1 minus P on your page. And then the n minus x, guys, is kind of like the complement rule again. How many total free throws were you shooting? 3. How many were you worried about making? 2. So that means you missed 1. I'm pointing to stuff you can't see, okay? Why this is more important is because when we start talking about 10 free throws or 20 free throws, because you have to shoot a lot, you don't want to have to sit here and think of all the different arrangements. It's horrible. So you let your combination take care of that. And then you know every probability of making one is the same, so just raise it to the how many you care about making, and then the probability of missing them is the same, okay? So let's see if we can do that on here. It says a card is selected from a standard deck of cards and replaced. Good, because if it wasn't, it wouldn't be a binomial experiment. This was repeated 5 times. So what is the 5 going to be for us? That's going to be our n, right? How many times are we doing it? That's our n. Find the probability of selecting exactly 3 clubs. So that's going to be our x. Notice, guys, we have 2 of the 3 things we need for the formula. The formula, we need n. We use that twice. We need x. We use it 3 times. What's the thing we don't have yet? P, the probability of success. What do we care about getting? A club. What's the probability of getting a club? I promise you this, like, we won't have cards on our test. What's the probability of getting a club? How many suits are there? 4. So it's 1 out of 4, 13 out of 52. So it's a 25%. Is that okay? On your test and on your homework, they'll like flat out tell you, you know, the probability of getting a free throw is 80%. Like they will shout from the rooftops that P, okay? On these notes, we just kind of had to calculate it. All right, guys, let's figure out the probability of x being 3. We're going to use this formula, okay? So we're going to have a big C in front because he's going to help us decide in how many ways we can get 3 clubs when we draw 5 cards, right? So when it comes to C, your n, how many total times you're doing it is the first thing. So we're going to put a 5 there. Is that okay? Because we're drawing 5 cards. Of those 5 cards, how many clubs are we worried about getting? 3. Times P, what's our probability of a success? 25%. But how many successes do we want? How many clubs do we want? 3. So we want 0.25, 0.25, 0.25, right? Or to the 3rd power. And again, I'm just following the formula. P is your success. X is how many successes you care about. So 3 is our exponent. All right. But if I'm drawing 5 cards and only 3 are clubs, that means I could get non-clubs, right? So what's the probability of not getting a club? I heard it, 75%. Is that okay if I just go straight to 75 and I don't do the 1 minus? Do you guys see what I did? So this is just the complement of 25, right? What's the opposite of getting a club? Anything else, which was 75%. So what's our exponent going to be up there? It is 5 minus 3, or 2. How many clubs did you want to get? 3. How many cards were you drawing? 5. So if 3 were clubs, 2 were not clubs. So again, I'm just kind of using, like I heard Brittany say the actual formula. N minus X. 5 minus 3, or 2, right? So this is just going to be, I'm going to put this in my calculator. Do you guys remember how to put that in your calculator? Oh gosh, I'm like throwing my calculator here. So in your calculator, remember you have to type your n first. So our n is 5. Then you hit math and you scroll over to probability and you go down to 3, our combination. So 5, choose 3. And actually we can put everything in there. I'm going to hit enter. So this is going to be 10. So that part's 10. And I wouldn't even probably do it this way, but I'm going to just show you the different parts. So 0.25 to the 3rd power is just 0.015625. And then 0.75 to the 2nd power. So I'm kind of just showing you all the bits, okay? So how many different arrangements can we pull 3 clubs out of 5 cards? There's actually 10 ways we can do that. That's what I'm talking about. I don't want to sit here and think of all those 10 ways. What is 0.25 to the 3rd, this ugly number? What is 0.75 to the 2nd power, technically, this number? I would just put it all in my calculator. You can, okay? So in your calculator, you can just type it exactly like that. 10, and then go to the probability, combo 3. Ooh, why am I not doing 10? I want 5 there, right? Thinking of the answer. Oh, goodness. Okay, so 5, combo 3 times 0.25 to the third times 0.75 to the second. And you hit enter. Is that what you guys got? You can multiply it like that too, okay? So most of these are going to be rounded to, you can't even see that, can you? Eek. Most of these are going to be rounded to 3 or 4 decimals. I always do 4, okay? So this will be, if you multiply it this way or all in your calculator, you should get 0.0879 or 8.79%, like if you wanted to change it to a percentage. Very, very low, but you guys agree that if you're getting 5 cards for more, the majority, 3 of them to be 1 suit is very, very slim. So we're not going to have very high odds there. All right, do you remember that I gave you that blue cheat sheet on Wednesday? On the back of it has an even faster way of doing it, believe it or not, where we can actually do binomial PDFs in our calculator, okay? So I don't even remember. What's the first move? Where are we going? Second bars, I think. So in your calculator, if you hit second and then variables, and you have all these like PDFs, if you keep scrolling down, you'll see 2 that have binomial. There's a binomial PDF and a binomial CDF. We'll talk about both, but binomial PDF is the one that you're going to use the most often, okay? When you choose it, it's going to be different depending what calculator you have. So mine's old. I think mine might be updated. No, mine's older. Okay. So mine looks like this. Those that have a newer one, you're kind of at a benefit because it flat out tells you what you want, right? I think so. On ours and the new ones, the first thing they want is your N, the number of trials. Is that what your guys ask you? What is N with the new one? Us, what we just have to realize with our old ones, that's what we have to plug in first. So we want the number of trials, which was 5, comma, and then the second thing it wants is your X, the number of successes. So how many clubs did we want to pull? 3. And then again, you're kind of answering these on the new ones. It's a little bit easier. And the last thing is P, your probability of success. So what was the probability of getting a club? 0.25, close off your parentheses and hit enter. Oh, what did I do? Oh, I did it the wrong order. I lied to you. As I say, it's the P's in the middle. That's my fault. I should have that blue thing in front of me, shouldn't I? So I hit second bars, and I'm going to go down. Sorry, guys. Those that have the newer ones, that's one benefit, is that you don't have to question the order because it asks you right off the bat. I'm sorry. So it's 5, the number of trials, and then it's P, your probability of success. And then the reason why they do that is because this is always consistent, right? You're always pulling 5. The probability of success is always 25%. How many you care about getting can change, and so I think that's why they have it as their last thing. We care about getting 3. And notice that it gives us exactly what we have. Like, we didn't have to use the formula at all. That will be true on the test, okay? I will give you the formula on the formula sheet. So worst case scenario, if you forget how to do it in your calculator, you can do it using the formula. But your calculator will tell you as well. So you can use calculator. Can use calculator. And if we write that note, will you guys know to go look for the blue slip of paper that has it, okay? So what would I want you to show me? Kind of like what you had to fill in, right? You would show me binomial PDF. You'd say N equals 5, P equals 0.25, and then X equals 3. And to me, that's showing you know everything that wants too. So I'm okay with you just using that calculator. All right, let's look at another one. These are probably more typical of what you'll see on the homework. It's not going to be these card problems. It's going to be like a real life example. So it says a survey indicates that 41% of women in the U.S. have reading as their favorite hobby. So guess what we can mark 41% with? That's our P. That's the probability of having reading as a favorite hobby. Anybody read? Do you read? Anybody else? Would you guys... Those that read, would you mark it as your favorite hobby, though? Probably. I'm kind of, okay, I'm the same way. Like, I don't read a whole lot, but if you ask me, like, what do you do in your spare time that's not watching TV, it'd be reading. Like, my husband likes to hunt or golf. I would be doing reading, probably. I think 41% is a little high. Like, I don't feel like we read as much as